Let me introduce myself. This is Prabakar. I'm working for the Government of India for the last 27th year, and I'm doing an MS Scholar in the National Institute of Technology, Tiruchirapalli. And this paper is co-authored by Dr. Srinivasan, the Associate Professor. And this paper is titled The Design and Development of a Smart Wireless Sensor Network-Based Data Acquisition System for an Aero Gas Turbine Engine. My presentation outline will be introduction, a problem definition on the instrumentation for a gas turbine engine, a proposed method for a wireless DAS, the results, conclusion, the future work, and some references what I collected. On the introduction, just to give a brief on a gas turbine engine, which is mainly having the compressors, which suck the air from the inlet, and then it burns the fuel in the compressor after this compression ratio of whatever is the engine design. And then the gas is expanded on several stages of turbine, thereby producing a thrust, which pushes the aircraft in the forward direction. A design of a gas turbine engine is a much complicated thing, wherein you have the best of all the possible fields of engineering to be available for a gas turbine engine. We do test the gas turbine engines mainly for the performance evaluation and the engine health monitoring. Here I am talking my experience on gas turbine engines, which is an Aero Gas Turbine engine, which is a developmental gas turbine engine. And the problem definition goes like this. You have the aero engines in the development phase being extensively tested on the test beds, the ground test beds, where you test the engine. And a typical data acquisition system, this engine is instrumented for more than 1,000 parameters of pressures, temperatures, vibration, flow, you name it, whatever you have it. And what happens is you instrument the engine, you have those signals taken from the engine, and then you run it across the transducers and the signal conditioners. The analog to digital conversion happens and the data processing. Typically, these are located in the control rooms. And from here, you draw lengthy cables to the control rooms. Consider simple 100 channels instrumentation and a 2-core cable for a single channel. You multiply by 50 meters per channel, and the overall 100 channels comes to 5 kilometers of cables. And suppose you have 1,000 channels, you imagine what is the kind of cabling you have to do to test this engine. Alternatively, is there any other way? Yes. If you can place the transducer, the signal conditioner, and the analog to digital conversion all near the engine, around it possibly, and then move into a wireless platform. On a trial, we have done it on Zigbee, and do only the final data processing and monitoring in the control room. Thereby, the whole issue of preparation of the harness, the laying and the routing of long harnesses, which involves high cost and extreme difficulty in maintenance and troubleshooting, which becomes easier with performing the signal conditioning and the digitization very close to the engine. The signal is further transmitted using wireless protocols and wireless sensors networks. So there are various works happening on Wsn across by biomedical, agriculture, military, and industrial, mainly for the efficient architecture of modules and the cost effectiveness and easiness to implement. This is being used everywhere. These days, Wsn is having an application on the safety critical applications like flight controls and health management also. So going to my specific work, what we have done on Wsn, we took temperatures and pressure channels for experimentation purpose. We took temperatures being measured by K-type thermocouples for the range of 0 to 1,000 degrees for a sampling speed of 10 samples per second, and pressures measured by pressure transducers, which has a 0 to 5 volts DC output, or a pressure transmitter, which has a 4 to 20 milliamps output, both are 10 samples per second. And the accuracy is required where as per the mil specifications, the military specifications, which are plus minus 1 degree up to 200, plus minus 3 degrees and plus minus 4 degrees above 800. And pressures, we have to measure at 0.05 full scale on both the cases. And we have configured a distance between the engine and the control room to be 50 meters. So the Wsn architecture basically has 3 modules: the sensing module, the processor and the memory module, and the communication module. The sensing module interfaces one or more pressure transducers to the appropriate signal conditioning circuits. The processor module, which mainly receives these analog signals, are having a processor, and based on the sampling speed requires and acquires the data, process for digitization, and then performs the digitization process, and then further sends the digital data onto the communication module, which through its transceivers, here in the case it's a transmitter, which transmits the process data to the receiving station. And here I have configured using a Zigbee protocol, which is used because of its low cost, ultra low power requirements. The overall schematic, we have a transmitter module and a receiver module, both powered by a power supply unit separately. We have the analog front end, the microcontroller unit, and the RF module with the transmitters. And then you have a receiver, a control unit, which further sends the data onto an Ethernet or a USB. The power supply module was configured with, to operate on a 12 to 24 volts power supplies. It has a buck regulator, which is configured to supply the low power requirement for the analog front end. And this whole concept of WLSN was designed to have a low power requirement, since the future idea is to go for a energy harvesting based power to suit this WSN module. So this whole module was conceived to operate on a low power device. The isolated power supply is derived from a low dropout from a 3.3 volts. And then the power supply is configured using LM25017. On the transmitter module, we have the analog front end, which is configured around AD7124, which receives the signals from the thermocouples or the pressure transducers and the transmitters, as the case it may be. The signals are configured as differential inputs, thereby avoiding any potential ground root problems. This AD744 is a 24-bit sigma delta ADC, which can be directly connected to the sensor. The resolutions are quite low. It can capture very low signals of the thermocouples which is coming. And the data sampling rate, it is capable of 2,400 samples per second. And then this is further connected to an SPI to SPI isolator module, which also has a 4-channel galvanic isolation to take care of the noise problems. And the processor module is configured around SAM L2 32-bit ARM Cortex M0 microprocessor within a 64-pin packages. Again, it's a low power operating with 1.62 to 3.63 voltages. It's a multi-channel ZART and a 256K flash, which is available over there. And this module is mainly used for the high data rate in a sub-gigahertz application. And it has an SPI to antenna solution, so that this is useful for transmitting the power. And on the receiver side, each receiver we have configured so that it can receive up to 6 transmitters. So each receiver can receive up to 6 Zigbee transmitters, and each transmitter we have configured for 6 channels. So that is the number of channels we can use. And we have, for the time being, we have used a separate USB power supply from the data acquisition system, which connects this receiver module to the data acquisition system. So this is the interface, what we have integrated onto a test engine, Aero engine. We have mounted 2 modules, one over here, one a pressure transmitter and a temperature wireless module. And this was connected to various signals from the engine. And from here, there is an antenna over here, which you can see. And this is a receiver module, which picks up both the things and connects it to a data acquisition system via USB. On the results, what we have done is, there are a 5-point temperature probe, what we call a temperature rake, which measures 5 temperatures at 2 angles in a particular plane. We call it as a compressor inlet plane. The 5 sets were connected to the regular DAS using the cabling, and these 5 were connected through a wireless through the WSN. And similarly, in another case, we have connected a 9-point pressure probe through the wired DAS and the 9-point pressure probe through a wireless medium. And the results you can see, they have a very close comparison with the scatters which are agreeable. With this, the conclusion was, there was a wireless sensor network which was designed and integrated into an Aero Gas Turbine engines, and the results were compared with the wired DAS, and both the results match very closely to the required measurement accuracies. A further implementation needs to be explored by improving the receiver capabilities and possibility of using WSN for a wireless, for a flight critical application. That's all. Thank you. Thanks a lot for listening. Any questions? I'm glad to answer.